You here?
Absolutely.
Amsterdam something.
Let's see. Wow.
This is your machine, right?
This is my machine. Thank you.
It was stolen.
It was
Really stole it out of my car in Berlin.
Wow.
So now I use my.
I hope no one steals mine. The university got it for me. I think it's not mine. The university got it for me.
Oh, yeah,
But
it?
okay. So this one is yours.
Thank you.
Morning. Let's wait there.
Good morning.
Yeah, I realized the CD from the web page is not active.
No, I'm sure it is not.
I also realized it.
So you're still affiliated with CFTI or no?
Yeah, yeah,
You are.
and with Nionic.
Nionic.
That's the two. More affiliated than on the
Okay. So here we have the Zoom. Here we have the presentation.
It works, yeah.
Uh,
It look nice, huh?
I'm going to start recording the meeting. What time is it? Oh, we start now. Okay.
Yeah, between
Maybe
a
a
few
couple of
minutes
minutes,
because the
thing.
people may not find it immediately.
Mm-hmm.
I have to search a little myself.
You're not also connected to the Zoom, are you?
No.
No. Okay. I just want to avoid any echoes and stuff.
No,
But yeah.
no, I close.
Cool. Okay. You're good to go whenever you wish.
Maybe we could do the paper, you know, because it's really hard to get in or get out.
I agree.
People may even hold on.
And then this is charging, this is plugged. Great. Okay. Cool. Can I give you some water?
Thank you.
It's your water.
You mean power?
That's one reason like that. Yeah,
Yeah, and like you should be able to say the microphone and you were working. I have the light, not the recorder. Or it's something like this. I'm just now verifying that it's working. Yeah, because some of the yeah. Yes.
Thank you for the nice tour. Hope you enjoyed it.
It was fun, yes, definitely unforgettable. Not a simple dinner.
That was the point. I think what we have in Netherlands water, so let's do that.
And food was tasty too.
It was very good.
It's not Dutch.
Maybe it was good.
But
it was not that.
fusion, sure.
Yeah.
My son.
Oh, okay.
Yeah.
I know, I mean, it wasn't here once in San Francisco when I was in Google. And, like a very good friend of mine, to be honest, and they're good friends, so I meet him sometimes. How is his startup doing?
Quite well. They raised 100 million.
Oh, wow.
Now, all the agent, the authors of the television papers of the
Yeah.
all agents.
Nice.
My daughter is still at Google. She's also.
Ah, she is, okay. Where? Good.
In Canada, she's mainly UX studies.
Everybody.
I should get the thing in presentation mode, huh?
Have you shared it already in Zoom?
I don't know. I think they did. I hope they did. Yeah, I think they did. I hope.
Okay. Can you connect to Zoom?
I think they did.
I don't know. Let
So
Yeah, it's not my machine.
I share screen, desktop. There you go.
All right, as we get prepared, thank you very much for being here today. It's a, let's say, side location of Amsterdam, so we're expecting more people to join, but you know, the day started, so we should get going. Today we have a bit of complicated logistics, space-wise, so we will be here in the morning. Then we will cross to the green building, which is the University of Amsterdam. This is a building that companies that do research with the University of Amsterdam use. And then we'll come back for lunch downstairs, and we'll cross again to continue the day again at the green building. So it's a bit of crossing between buildings to taste the weather. It's just like 1 minute walk. Yeah,
Just follow you.
Yeah, exactly. So yeah, it is.
Thank you very much. Good morning, everybody. I'm really delighted to introduce the first speaker for today, Professor Hans Uskoreit. This is one of the most experienced researcher in Europe and probably in the whole world. So we are very proud to have him here. And his current affiliations are a large language model startup, Nionic, and he is affiliated for many years and has been scientific director at German Center for Artificial Intelligence, currently in Berlin. So Hans has very close ties to China. He has co-founded various startups and served in principal roles in various institutions. And today he's going to speak about foundation models from a European perspective. I'm very thrilled to listen to your talk, Hans.
Thank you. So, first a warning, this is not a scientific talk. I'm still doing some research, but not the type of research that you publish. Or mainly the stuff for getting something to work, yeah, and then be glad that it works and forget about it. The connection with foundation models came very early, pretty quickly after the transformer paper, the attention is all you need paper. We already used there. We already saw interesting improvements because I had worked on MT evaluation myself, and then we used BERT and later MT5 in our company in order to fine-tune the system. So we had an older system based on discrete relation extraction, discrete learning, machine learning, relation extraction based on dependencies. to get data. And if we had enough data with the one method, yeah, then we bootstrapped and then we fine-tuned BERT. And that was the first time when I was kind of surprised, because I sensed early signs of seeming understanding. You know what I mean? That the system really in relations, even if they were completely different formulated, yeah, from our patterns, it could detect them. Yeah, and so that gave us to think already very early. So then after GPT-3 came out, we thought that is now the time. Yeah, now we have to do something, but what can we do? We don't have any infrastructure in Europe like that you need. And then together with other people, we formed an initiative in Germany, which we called LEAM, L-E-A-M, Large European AI Models in Germany. That was something together with other companies. In the beginning, it was with AI companies. And we worked out some kind of a plan. What would we do for European multilingual models if we had the chance? Yeah, which other data would we use? What would we? So, but we still didn't have the chance because we didn't have the infrastructure. And so we made a plea to our government. And I tell you more about this story. But first of all, I mean, you know, this year is many models. It's probably not complete. Yeah, this is the model starting. It only starts with the T5 and then goes and doesn't even have the latest on there. And those are the models that come from the US. The red ones are the ones that come from China, and the green ones are the ones that come from Germany, things like Bloom and Luminous of Aleph Alpha, and of course the models of stability, yeah? So the stable. And so that looks a little bad for Europe, right? I think, as a European, I have to say it doesn't look good. And so what can we really do about it? We don't have hyperscalers of that sort we don't have a Google and we don't have a Meta. And so what did we try to do? We tried to convince the big German companies like SAP, the largest the largest European IT company. And they said, no, we are more like Oracle. You know, Oracle doesn't do their own big model. We are more like, so no, we let the others do it. Yeah. So it was really difficult. So then we talked to the government. Wouldn't it be possible? Because also research does not have our researchers in Europe. Yeah, they don't get the training and they don't get it. And East yesterday he gave a very good talk, Alan AI talk, and he made a strong case for researchers trying to do and experimenting on the training part. Yeah, and how can we do it without the infrastructure? And also the same is true, by the way, for the US. Also in most US universities don't have large models. They don't also have like the infrastructure. So, but what did they do? So Oren Etzioni and others, they were called on a task force by the White House, and they made up a plan, and it took them also a while, not quite as slow as Europe, but in January they offered this plan, and now there is a new legislation to be presented to the Congress. Yeah, that came out of it with 2.4 billion. Yeah, to improve the infrastructure for universities. So it's something coming out. But what do we do in Europe? In the meantime, also China caught up. And it's very difficult for us from Europe, but I have been in China very often because I had a company there, and now I will tell you the latest also. And now there are 12 government approved. Those are only the government approved systems. So they passed quickly in July, they passed a law demanding that any model that would be released to the public, only those, yeah, need to be certified to be sure that it says the right thing, yeah, so at the right place. And so in the beginning, 8 models were certified, and then 4 more. And this is now not all of them are from hyperscalers. Some are already from newer companies. So, so why can't we do it in Europe? We don't, don't we have the right talent? But wait a minute, these people are not American. All three of them are not, yeah? So so if we look, this is a name list of people that I used. I once took a reading from a course that was all the stuff that went to deep deep learning, yeah, pre-deep learning and deep learning. That was already some years ago, and then I checked for fun, just for fun, because I was always asked, "What about talent in Europe?" I checked where the people came from, yeah, originally. And I saw there not so many Americans there. So the Europeans are not doing very badly. Yeah. So, but usually not in Europe, yeah, because, well, we don't have the infrastructure. We cannot keep the people. And then I thought just recently, oh, there's an outdated list. So I take any random list from I really random. I checked some list of eminent people, of important people in the field, and picked the 40 AI researchers to follow in 2022 by Medium. And again, this is the blue ones are the Americans among them. Yeah. So people come from that's not surprising. It's a big brain drain. Yeah. It's a big brain drain. So, but why couldn't we do things in Europe? So we got then lots of support from other organizations in Germany, large companies, they all support us, small companies, industry associations, the German Informatics or Computer Science Society, everybody is behind us. Everybody is behind us. And then the government gave us a task. Yeah? They gave us money and they said, you make a plan. Yeah, so like governments are, they want to do things in an orderly way, yeah? Not just move and spend money, first make a plan. So we did a feasibility study, 250 pages. You can look at it on the web. It says it's a blueprint, and many experts, among them even some in the room, like Irina, helped us. Yeah, so lots of people helped us. So we made a solid plan how to do it, and after that, in January, we presented it, and all of industry praised it, and the government thanked us very much, and they said, "This is a wonderful plan. We urgently need to do it, and we need to do something soon and fast." And then they said, but maybe not for this year, the budget is already made, but and next year we may have a problem with energy and Ukraine, and but we will do something. Yeah. So a while later, they invited some people, among them Richard Zocher and others, to a cabinet meeting. Fei Xu was invited from SAP, who was at the time leading SAP AI, and they were all going. Some people, mainly former students of ours, but by coincidence, and they were at the cabinet, and the whole cabinet said, "We need to do something, yeah, and fast." I mean, you understand, this year is very bad for us, but financially, yeah, but something needs to be done, and quickly. And so then some weeks later, then some AI researchers, among them again Fei Xu and some other people, also colleagues and former students of ours who are now running big AI enterprises, they were invited again to to the Chancellor Scholz, yeah, to an evening dinner on AI. And Chancellor Scholz was very clear that something had to be done, yeah, but it would be difficult to do it right now. And so you can imagine how the story went. So at this point, then we had this report, yeah, and we did everything, and we showed exact blueprint. We got kind of frustrated. So my son, who is also an AI, he told me all the time, he said, "Dad, you are losing your time talking to the government, yeah? Try to get private money." So don't try to convince the government. And in the end, and I thought, no, I'm too old for that, not another startup. I had already several, and I'm glad that some of them were successful and be sold, so not another one. But then what could we do? So then we started another startup. Yeah? So we did Nionic, and turned out that there was a former student of mine in China, Han Dong, who already ran several successful companies, and he worked at Rocket Internet in Berlin before. And Johannes Otterbach, who was at OpenAI when GPT-3 was trained. He's a physicist, worked earlier in quantum computing in Harvard and at Palantir. And Fiyu left SAP because she couldn't convince SAP to do something. So she said, okay, then she goes to the small company and wants to be there. And also the CEO of the AI Association, Vanessa, helped us. Yeah? So she also came to our company. So we started this company in May, and there we are now. Yeah, we are trying now very hard. So, and we are often asked, why do we need so many AI models? Yeah? Whenever I show all the AI models, isn't one AI model that does? And this I don't have to, probably not in this audience, I don't have to go through. I mean, you know that it's ridiculous to think that one model would master the 2,000 written languages and be knowledgeable with all parts of even specialized knowledge, and be explanatory, and be truthful always, and be creative, truthful when it's needed to be sticking to the truth, and creative when it's needed not to stick to the truth, but to make something up, and ethical for everybody, for the Chinese government, the American government, the German government, and all of us, all the churches and all the religions. Yeah, this is exactly. So this is, I mean, this is, you saw when at one night the stock of Google dropped quite a bit because the system couldn't answer some questions that most people also cannot answer. Yeah, we are waiting for God. Yeah, we are not waiting for. I mean, what people want is they don't want super intelligence; they want godlike intelligence. Yeah, if everything. Yeah, so you're right. So. There are many observations that we made now. We tested many, and only to share some very, very quickly with you. Yeah, I mean, you know some of them yourself. So we applied then two models in order to find out what we need to do. For instance, the CEFR proficiency tests. Those are the 6-level tests, like, you know, the A1, B1, C1, that are kind of standardized within Europe, but also the Chinese, for instance, the HSK follows the same 6-level thing. So, and we tested the comprehension part and saw, not surprisingly, that many of the models that are very eloquent when it comes to comprehension, serious problems. Yeah. So then we tested things across languages. Will the system give us the same answer? So if you asked GPT 3.5 in Chinese, my application to the Communist Party has been turned down. What can I do? And if you ask the same question in English, you get totally different answers. Yeah, in the English, the model will tell you, oh, it's an authoritarian party, you cannot do anything. In Chinese, it will give you exactly all the steps that you need to improve in order to. So that's not a surprise. Yeah, or there's a metaphor in Chinese saying "lie flat," which is mainly a movement among the young people who refuse to be in the rat race of competition and get out of. And if you ask in Chinese why youngsters want to lie flat, they tell you, oh, this is a metaphor for a certain. If you ask in English, they say something like maybe they are tired, or maybe they need some break. So why people like to. So you get complete, but that's known. So then we checked also sources of hallucination. Very interesting. Yesterday, there were nice cases. And we found out that the most frequent type of hallucination comes, and that should not surprise us, when the system, by the statistical evidence of what it learned from, thinks that it should say more in a biography, in a list of things, but it doesn't have knowledge about more, but because it's not driven by truth. It's driven by trying to formulate a text that is most similar to the situation that it should do. Yeah. So, for instance, give you things that several people, like a friend of mine and also Wolfgang Wahls, the AI researcher in Germany, former boss of mine at the DFKI, he was declared dead by the system, and also a friend of mine was declared dead. And I was very shocked, actually, when the system, I had a friend who was a singer in New York, yeah, and when the system told me that she's dead, that was at the end of the pandemic, I thought, oh, she died, and I was really very upset. And then I found out she hadn't died, it was a hallucination. Then we compared, we found other cases, and it's always when people like Wolfgang Walzer retired, before he had lots of things, then he retired, there was a gap coming. Yeah, because the same with the singer. She had records, appearances, pandemic, gap started to come, but she's not that old, so system made up, no surprise. And the same thing came with other things like product lists. And so whenever something, let's say one company has lots of products, the other one has only 3, oh, then the system makes them up, yeah, some other products that have to come. So very interesting. So then different levels of explanatory capacity. Some systems, if you ask them, we had lots of test batteries, yeah. When you ask them a miner strike in Congo, yeah, what does it have to do with BMW? BMW was one of our customers of the company, and we delivered news to them, relevant news every day. And so what does it have to do? And GPT-4 was pretty smart, said, oh, in Congo, cobalt mines, and BMW works quite a bit on batteries, so it's very important for them. Yeah, another system by a German company, which I do not want to mention, said, what does it have to do with BMW? It says, oh, the miners cannot get to work. The miners drive to work with BMWs, and so which is in Congo not so powerful. So that look different. So and then but this is the last one is the most important. The others are just anecdotal. The last one is really important. Insufficient specialized competence. That is what we tested. So when companies gave us indicative benchmarks to ask, what is important? How would they test if somebody is suited already is up to the tasks of the company? Yeah, it was not good enough. Even if it's good enough for undergraduates, yeah, it can pass all the placement tests, you know, all the statistics, right? It is not good enough for the industrial knowledge. How much do I do time with? Oh, then I jump over the garden path stuff. I did wonderful stuff. I mean, for another time, yeah. I got the system in talks and making up garden path sentences and tested how it got it. Very, very good. But no, I jump over all that stuff in manufacturing industries and come close to the conclusion. Oh, but I started very late. Okay, so you know, 5 minutes. Yeah. So you know, in industry, with normal AI, yeah, with normal AI, what I mean is supervised models, yeah, that don't have emerging capabilities. You get, this is mainly lots of tasks, yeah, 3 things, mainly classification, then prediction stuff, and then robot kind of steering. That is so 3 classes. Huh? So now, but there is much more in industry. So now add the text stuff. The text stuff, our models are very, very good at, the language models. Yeah? But then there's lots of other stuff like generation of code, then the conversational stuff. And then down here, this is really knowledge savvy applications. This is the holy grail. This is really what will help companies down there in the end. Yeah. So what happens now is what you can imagine. Here in the middle, it can do everything. Yeah, the systems can do everything. And they do already a little bit on the conversational side, but so far they are not usable for most things, and only for very, very few industries that happen to have enough data coverage and are considerably simple. It can already help down here when it comes to decision support and so on. And that's shouldn't be surprising. And the red thing should indicate this is stuff that eventually the systems will do. Why will they get into, I mean, you know the answer. Why will they get into the stuff that can be done by supervised learning? because the same thing that we experienced in our former company in Giants, when we fine-tuned the system, by fine-tuning it and telling the system what the numbers mean that you do prediction on, they can integrate it into their stock of knowledge and see, like for instance, the cobalt stuff with the mining and lots of other things. Yeah. So the system gets the connection to other types of knowledge. Yeah. You give it a table. Normally you would only give it a task of prediction, yeah, on the, not predicting next word, but predicting the numbers, yeah, the next numbers for next year. But if you connect them and tell the system what it is, that it is the demand for certain spare parts in a certain field, then you get out the connection. Oh, it was especially high in the summer months, yeah, because then the system will connect it and will say, this is something having to do with air conditioning in a car, especially in the summer months. And so that's so for even for fine tuning. Okay, but I need to. So where do we stand now? And then I finish. We have here in Europe a lot of talent. We have companies, projects, but we still don't have a sufficient infrastructure, even if we have Leonardo and Lumi now even used by Ellen AI. Yeah? So there seems to be infrastructure. We still have a very serious shortage of GPUs, and it will increase. Right now, strangely enough, you get the cheapest GPUs in China. They are not supposed to have the A100, but they were not dumb. Before the ban was issued, they bought lots of them. Yeah, so all of the companies. So you get the cheapest right now, the cheapest compute for big model building you get in China, we know. The second is the US, and Europe is very, very far behind. And then we have insufficient cohesion and coordination among European players. We have very good companies like Silo AI in Finland, Aleph Alpha Stability. Now the new Mistral, they came up with their 7B model, which is kind of still good. Yeah, it's not yet terrific, but it's pretty good. The Light-On in France and our Nionic, we are now working on our 7B. So far it looks good, but we have to see. And scaling up. So what can we do if we really want to change something in Europe? Yeah, because I mean, I mentioned already in other parts of the world it looks different. So even in the United Arab Emirates, yeah, with Falcon B, they got a system, and they trained a system of a size that usually none of you can train immediately because you don't have the infrastructure. So we need to get together, yeah, and approach national governments, European Commission, large European enterprises, and powerful foundations. And so, I mean, you may think this looks impossible or is very far advanced. I can tell you it is not, because actually you do not have to convince, I told you, you do not have to convince the governments anymore. It's only a little more pressure because they are convinced. They know it very, very well. European Commission has invited us. They know it very well that they need to do something, but they say, oh, we formulated our work program already in the horizon, you know how long it takes and to change and the next version, and before we cannot do much. But they all know, and they could all contribute and help. And moreover, right before I came here, I talked to a group of people I never talked to. Those were about 25 CEOs of very, very large companies, all companies of Fortune 500. Yeah. So I got to talk to them about it. Yeah. Gave a talk and had a keynote there. And lots of them came later and said, why don't we do something? Yeah, especially the Europeans, after they saw my slides, they came, said, we have to do something. Yeah, why don't we? So because each of them does it on their own. Yeah, so and I told them, maybe if you go together and issue and help to do this little push more of the government. The government already knows they need a little more push, because right now they get the push from the energy people and from other sides. Yeah, there are lots of people who want scarce resources. And one more thing, and then I finish. Another hint, something that my son already suggested a while ago. It's large foundations, private foundations that are interested in Europe, and they want to do something revolutionary that leaves a footprint. So the Wallenberg Foundation, family behind Ericsson, you know, they did quite a bit in Sweden, yeah, for GPT-SW for the Swedish part, and they gave the infrastructure already, quite not good enough for much larger, but for that, yeah, they did quite a bit. One of the persons I talked to when I gave this talk to all these people was Jacob Wallenberg. Yeah, he was also there, and there were many people of that sort. And he said, and I told him, I said, your foundation, now all researchers in AI in Europe know about you because you did. And he smiled. He said, yes, but what can we do now? And then I told him, get together with the other foundations, and because they are meeting also, like we are meeting, they're also meeting, and get and do the next steps. And he was very into it. He said he will follow up, and many of these other people want to follow up. They are, it's not lip service. I think they are really interested, and lots of people are close to making these decisions. Now we just have to be united, yeah, and come together. So that was the last word. I usually close that when I finish, but this is Zoom. I cut off the other people. So.
Thank you. So unique opportunity to ask private questions. Yes.
I agree with what you were saying, but the one thing that I'm missing, and maybe you're not ready to also give this away, is like, but I think if we start trying to go big in Europe or something like this, it should not just be a clone of, not to be exactly the same approach, but just apply to.
I give you some. Exactly. Thank you. So now, because I dropped one thing that I mentioned it yesterday already. There are several things. One is we could start from the inside that I mentioned yesterday, that right now, and that was also in the open AI talk by that now, although we still need to work on the architecture, new architecture, but just doing the other part, working out better training, there will be a new field, not machine teaching only, but it may be called technology education or something. Because that requires really a different type of knowledge and a different type. If you want to work for the purpose of industry, the computer scientists working at training the regular people who know about the algorithms and machine learning, they are not enough. They don't know anything about the industrial knowledge. They don't know, they sometimes even don't know what the difference really, or exactly what the difference between doing classification and Library of Congress and the German National Library and all of these are. They have no idea about this content stuff. They don't know how to evaluate. They don't know enough about the open access. If we look at some of what the American models did, they didn't take into account lots of data that we had collected in tens of years or more than 10 years in Europe for all languages, because they can only be gotten if you register and download thousands of files. So they are not in there because you cannot get them via OpenCore. Lots of open access books and journals are not in there because they took things like PG-19, yeah, the books up to the year 1919, and books 1 is mainly unpublished books, self-published books, not of the highest quality and not very much industrially relevant stuff among it, because they are all self-published. It's very nice that the systems now are very good in novels, yeah, But so if you take a new stance, so do more the language stuff and do more controlled, that was exactly what is yesterday said. So, if you do more controlled learning, stuff like that. So, and more on the need there on instead of trying to do, I mean, yes, you need also but you don't get enough start already from these people.
Yeah, so but you try to invest more in making cases, making especially feels to me that you're always kind of exporting stuff, but never kind of when it was cheaper to make always disruptive reviews and stuff like that.
Maybe, yeah, this is now the world is unfortunately not, or fortunately so much interdependence of one country, the Netherlands, makes very valuable stuff for the reporters. Another country, maybe Taiwan, makes something else, and in the end, it's no individual country anymore. I think it doesn't matter so much where the final chip is produced. You know, all the ingredients come from different countries, and whether now they are done by Taiwan or in a factory in China for Taiwan. Done by a good firms if you understand, yeah. So yeah, we can play a role in the army. That's right. That's another thing. Of course, the industries that create the AI chip of tomorrow chip that very much supported. But that is not for immediate. Yeah, that takes such a long time until you can get harvest so we need to do that in parallel, but we cannot wait until the new generations of chips.
Wonderful and inspiring software. So what worries me is that like as scientists don't talk to AI. I don't know what people are talking about, but they're just inspired from making it. However, I have a feeling that at the government level or policy level, AI is primarily seen in negative. As a threat somehow, either like
I didn't have time to talk about that. I have to talk about that, of course. Yeah, you're absolutely right. I mean, yes, and because this is there, and the people governing, especially in Germany, the Social Democratic and the Green Party, have lots of people among their voters. That is another thing why they can then say, oh, let's maybe think a little more longer. We have a chancellor now who hopes to solve many things anyway about long thinking, yeah? And yeah. So like that is a danger. That is also like the AI regulations that we talked about yesterday on that you see more than
that's one. Nothing is, for instance, in physics, we all have to follow like CERN, like it was like a massive volume going there.
Yeah.
Primarily, it's the first positive message, you know, we don't understand the universe. Also mysterious what's going on there. So, do you believe that AI needs equally positive message? That is inspired.
Yes, that is exactly there's a whole group within ELLIS and Claire that has drafted plans for AI CERN for Europe. Yeah, that actually is already an existing concept that they are trying to push very much. The problem is the sustainability question, the climate change question is getting into our way there, because the countries that are more likely for being the hosts for such a CERN are the ones that have terribly expensive energy right now. So there is now this new green model training infrastructure company in Sweden. I forgot the name. There's a new company in Sweden that they try very much hard to do only things with green energy. And I was pushing another concept also when I talked to the CEO, very briefly on that. There's one good thing about training. It needs to be done massively, but if you interrupt in a controlled way, nothing happens. So if you don't, it's not a, so what does it mean? It means that for renewable energies are, it's not that they produce not enough energy, they produce not enough at certain times. In other times they have too much. So if you can have in Europe a training facility that uses exactly, that adapts to the over and under production of the renewable energy, we even give them some advantage, because it's not so easy on the grids, the overproduction at the spike times. So I think we just need to work it out.
When learning even at the physical level.
Yeah, thank you very much. Hans, you definitely need to find time to write a book. Document all this. Now we move to the second talk of this morning session by Seiji Benai. Seiji is an assistant professor at the School of Computer Science and Engineering at the Hebrew University of Jerusalem, and his previous affiliations as a postdoc are at the University of Copenhagen and Pioneer Center for Artificial Intelligence. His research interests are in computer vision, machine learning, and computer graphics. In particular, he's interested in generative models, neural signal representations, and inverse graphics. And his talk today has the title Towards a Controllable Generation of the Multimodal World. So thanks for joining. We are very much looking forward to the talk.
Thank you very much for the introduction. Just checking you can see my screen and hear me well.
Yep. Yes.
Perfect. Okay, perfect. Yeah, so thanks very much for the introduction. Just as you mentioned, I've just finished my postdoc with Serge Belongi and starting now my assistant professorship at the Hebrew University. Very excited to talk to you today. Wish I could be here in person, but as you may have heard of due to the security situation, unfortunately, I couldn't arrive in person. But I hope in this talk, I hope to give you sort of my perspective on how visual foundation models can be sort of used to enable controllable generation of the multimodal world. So this is going to be more a talk on sort of visual foundation models. Okay. Okay, so we've all sort of recently witnessed this revolution in generative AI for 2D imagery, and here you can see a few examples from such models such as Stable Diffusion, Imagen, and DALL-E, and these are sort of a great example of controllable generation, but where you know, the control is in this case just given through text. And ideally, to have sort of a full control of the visual world, we would like to sort of both control semantic information in images and videos beyond just text. So this could be segmentation maps, the relation between objects, dense captions, and so on. And we'd also like to sort of consider the physical or non-semantic properties. So you can imagine that images and videos are really projections of the physical world. And so we may wish to control properties such as object intrinsics, such as shape, materials, and appearance, object extrinsics, as well as scene properties. And so controlling such properties, I think, could have potential to be transformative in almost every application we can think of. So just imagine you want to sort of redesign your living room, and you might want to sort of control physical properties such as texture, materials, lighting, and so on, but also semantic properties such as the arrangements of objects and so on. So how can we enable this sort of control in these generative models? And just putting here a few more applications that I think are transformative. And sort of I divided into sort of two things, semantic and physical properties, and I'm going to sort of start with the semantic part. And hopefully by the end of this talk, I'm going to sort of lay out the roadmap that I think we should go in order to achieve both physical and physical, semantic and physical control of images and videos. So one important class of generative models you're probably all aware of is that of diffusion models, and we've shown impressive capabilities. And this is an example of stable diffusion, which has been very popular since it came out. And this is an example where you'd condition the diffusion process during training. So in particular, you would condition the sort of through cross attention mechanism the activation of a denoising unit. But this sort of requires you to, each time you have a new condition, you need to sort of retrain your stable diffusion network. So what can we do during inference? At inference, we can do we can either fine tune those models, or we can sort of guide the noise process differently. So ControlNet is one example which sort of modifies the network architecture by sort of duplicating network blocks and connecting them through zero convolution. And then you have an auxiliary module that takes some conditioning C, and it allows the model to learn control handles. Other methods, such as classifier guidance and classifier free guidance, they modify this score function in order to enable, in order to sort of predict the noise at each time step towards the desired class. And this is great. It works quite well for a large variety of cases. This is an example from ControlNet. However, there's still some issues with conditioning diffusion models this way. So for example, if I say something like a photo of an iron, that can mean two different things. Does it mean the iron metal, or does it mean the iron that I use to iron my clothes? And so there's some issues with lexical ambiguity, as well as with the ability to generate fine-grained details. These generative models are pretty good at generating coarse details, but when you want to specific fine-grained categories, that is still problematic. So how can we solve this? Well, we can think of a general setting of text-to-image models as sort of taking some text and coding them into textual tokens, and then passing them through a generator, right? So if previous methods sort of modified the generator to achieve this conditioning, we can instead freeze both the generator and encoder and simply modify the textual tokens to achieve our desired intent. So more specifically, instead of guiding the diffusion process or updating the entire model with a classifier, we can only update the representation of a single added token corresponding to the class of interest. So in this case, a target class. Then we iteratively generate new images with higher class probability according to the pre-trained classifier. And so by including this new sort of learnable token, we can really improve both text-to-image alignment as well as lexical ambiguity that you see here. And sort of the ability to adapt textual tokens is actually quite general. So for example, we can take other modalities such as audio, use a pre-trained audio encoder to map them to some audio tokens, and then map those audio tokens to textual tokens. And so this approach is pretty general in the sense that we don't make use of the fact that the generator is at all a diffusion model, and we keep the original capabilities with respect to the input text. So here you can see a few examples. And since we mapped audio tokens to textual tokens, we can also sort of combine both textual tokens and audio as well. So you can see these two examples here. And this is nice, but you can see that there's still a lot to improve, right? We can sort of do a much better job at modeling the physical properties here, such as the drums and so on. And so this leads me to the second part of the talk. So we discussed how we can sort of enable semantic control But what about the physical control? So kind of, again, we imagine that images and videos are really just projections of the 3D multimodal world. But in this case, if we just want to sort of train a large model like a transformer or diffusion model, that is not a very good idea because these are sort of very data hungry models, and it's pretty hard to get supervision in this 3D multimodal case. So instead, we can make use of strong physical priors or inductive biases about the real world in order to sort of design disentangled physical models of the world. And this has been pretty popular in traditional computer graphics. And sort of recently, this approach was combined with neural approaches such as neural rendering, where this is essentially a methodology of taking disentangled representation of the physical world, such as a 3D scene, rendering different views, and then we train our physical model in a manner that sort of matches our observations with those images that were rendered from the scene. So NERF is a great example of that, and that's great since we can sort of incorporate good priors and therefore avoid the need for a really large data set. But the problem is that we really have very limited 3D or multi-view multimodal data. So instead, what we can do is perhaps use the visual foundation models that I've sort of introduced in the first part of the talk. In particular, how can we use the sort of controllable foundation models that are conditioned on semantic information. And that is nice because now we have lots of data on which these foundation models were trained. So I'm going to just show you a few examples of this. So for example, here is the first demonstration of this concept. And in this project, the goal was to stylize an input 3D object using text. So the input was a mesh, you can see on the left. And using a text prompt, we were able to sort of stylize the input mesh. And to put things in perspective, I think this field has sort of blown up in the past year or so. So there's been a couple of concurrent work that has also enabled text to 3D or text to 4D, and so on. Just to point out a few things. So for example, we can sort of hallucinate all kind of interesting physical properties such as muscles, clothing, material, variety of textures, the ability to hallucinate lighting, as well as to produce out-of-domain manipulations. So this example of astronaut course. So how do we do this? Well, the input method is a 3D object represented using a mesh. And you can think of this as the disentangled physical representation because you have the separation of content and style here. We then train a network to sort of produce the style for every point on the mesh. And more specifically, given an input point, we pass it through a neurofield that predicts the color and displacement. And for each, and that sort of provides us the style of the given point. And more specifically, for the input point, the color is changed to the predicted color, in this case red, and it is also displaced along the normal at distance d. Okay, so the next step is simply to pass it through a differential renderer that gives us different multiple views of the stylized mesh. But remember that now we don't have a sort of multi-view supervision. So what can we do instead? Given the input text, what we can do is simply pass it through what we want to do is simply to match the similarity between the rendered views and the input text. And the way we can do this, once we have the similarity, we will be able to update the neural network to produce better stylization. And there's sort of there's many ways we can sort of produce the similarity between the input images and text. But I want to mention two ways, and one of them is through CLIP that you may have heard of, and And essentially, this is a network trained on many pairs of images and text, and so as to produce, so for example, in this case, sort of matching the similarity between a photo of an airplane and the text of an airplane. And so we can use this as a pre-trained network to define the similarity between our rendered views and the text. And another way, and I'm not going to go into this, was introduced by Dream Fusion, and essentially it's a way to use a pre-trained diffusion model in order to see whether an input image, rendered image, matches a given text prompt. And so this really enables us to use those visual foundation models as a way to get a similarity between images, and therefore we don't need any 3D data set in this case. So just showing here a few more examples, we can also sort of increase the granularity of the text, as you can see here. And since we measure, so for example, something like clip can enable not only the similarity between text and images, but between two images. So we can also stylize our mesh given an input image in this case, as well as through the rendering of another mesh. So this allows us to take the style of another mesh and produce a consistent stylization for that mesh. Okay, so this again is an example of this framework, right? We started with this disentangled physical scene representation. We rendered multiple views, but now we didn't need corresponding observations. We simply used a visual foundation model to give us this sort of similarity between text and images in this case, and this enabled us this kind of the ability to stylize 3D objects. I'm just going to show a few examples here without going into more details, but we can also we extended this approach also to dynamic objects, so objects within video. So here you can see a few examples, such as this dog, and you can see that the ability to produce sort of consistent stylizations of objects in videos. And we also looked at the case of sort of shape manipulation. So imagine that you have a volumetric representation such as a nerve. Then if you have a representation of the full scene and the background scene, you can really sort of do arithmetic within this disentangled scene representation. So if you have a full scene, you can sort of subtract the background scene, then separately manipulate the foreground object, and then put it back into the original scene. So here you can see a few examples. You can sort of do this arithmetic of volumetric scenes and then modify objects separately, such as enlarging the TV or manipulating the objects here. So I think I try to show a few examples here of both semantic control of images and videos, as well as how we can enable physical control. But there's been a lot of research beyond what I've just shown. So to enable this sort of full control. But I sort of just want to paint a picture of what are sort of the challenges and where we should go next. So going forward, I think there's a number of challenges. First, we wish to build a disentangled representation of the world that is multimodal. So observations should sort of go beyond images to also sound, touch, or any other modality that we wish to interact with. Given these observations, we wish to sort of produce a disentangled physical scene representation of the world, which we can then sort of differentially render and then match with any observations that we do have. But these observations are really partial observations, right? We have to sort of find a way to fill in the gap, and that's how we can, and so we can sort of fill in the gap using visual foundation models, in particular visual foundation models that are conditioned on some semantic information. So this could be any prior knowledge you have about the scene, such as whether that's a scene with drums or something else, but these semantics could also sort of come from our observations that we have. Another challenge is in the fact that if we have only partial observations, you can think of this as having infinitely many models that sort of are consistent with these observations. So ideally, we would want this entangled physical scene generator, the ability to generate all the possible disentangled scenes that are matching our observations. And we should hopefully be able to distill visual foundations to fill in all the possible missing information this way. And lastly, and this is part that I didn't talk too much about, I think that we want to enable this sort of seamless interaction of this physical generative model with humans. So humans should not need to say, I want a specific texture, I want a specific physical property, but should say something, I want a cozy living room. And this should be able to translate into both semantics and observations that are used to condition our a physical generative model of the world. So with that, I'll be happy to take any questions.
Yeah, thank you very much. Questions?
Very cool talk. I wanted to ask, you have shown some examples of basically training a small part of this of these large foundation models, for example, only training the tokens or only training the differentiated renderer, if I understood correctly how that worked. So
I can barely make up what you're saying. I would appreciate if you could either repeat it or.
Sorry, you want me to repeat?
Yeah, I can barely hear you.
I will repeat the question. It's because I think this is not connected. Sorry, I will repeat the question for you.
Thanks.
So you have shown examples of training a small system basically that interacts with a large foundation model. My question was, how do these how does this kind of training regime work in the low compute, low training time kind of scenario? Because it seems like there's a lot of potential here for exploiting these large pre-trained model and being able to do things without having access to incredibly big resources.
Right. So just to repeat the question, if I get it right, so you have shown examples of training smaller networks to interact with the foundation models, with the larger models, and the question is essentially in such a low computational setup, how can you actually do all this training to show interesting results in this interaction setup?
The question was a bit like basically asking like how well do these systems perform in a low
how well do these systems perform in a low computing setup?
Okay. I think what I've shown is the examples I've shown are sort of optimization based. There's a challenge of, I think, making them feed forward in a sense. So I guess in that sense, if you're talking about sort of speed or something like that, that's still a challenge in the sense that this optimization is going to take you, I don't know. For example, the mesh example I've shown is maybe 10 minutes or so per scene. So there's a challenge of that. But in terms of memory requirements or things like that, then I guess sort of we do the optimization per scene, so that it's not too expensive in that sense. But and especially the visual foundation model is fixed in that case. We only want to sort of distill the information we already have from a pre-trained visual foundation model, as opposed to having to train that. So that's another challenge in a sense, an advantage, I guess, in the sense that you can sort of separately train your visual foundation model and then sort of distill the information from that into your physical model, if that makes sense.
Makes sense. Thank you. Any other questions? Yes.
I'm speak here.
I guess that's easier. Well, now I'm very prominent. I think it was very interesting talk. One perhaps a question that I have is how physical is it really, in the sense that okay, you're of course putting things into a renderer, so this is actually mostly geometric. It doesn't really account for the physics or the mechanisms of the world in that sense, which means then that basically you're tied down to the implicit biases of the people that made the renderers in the first place. So is there any place, in your opinion, for causality or for sort of interactive learning, interactive with the world, I mean? Yeah, any comment would be interesting to hear. Yeah, thanks.
Yeah, it's definitely interesting. The way I think of interaction is actually through inputs to the system. So you can see here on the left, like this interaction via LLM. So we shouldn't assume those models are just getting a fixed set of observations or things like that. But this could be sort of iteratively changed with the sort of humans saying, okay, maybe I'm saying one thing, or maybe I saw, you know, a few examples of I don't know, of a particular scene, but I should sort of be able to interact and edit those observations, if you like, to sort of match, to give me a better sort of a less biased version, perhaps, of what we want to show. But yeah, I mean, ultimately, in terms of causality, I think that's the way you design your disentangled physical representation should be causal, in the sense that any, you know, for example, when we talk about the way light interacts with material, then this sort of, you know, these are causal physical factors that explain our observations of the world. So in that sense, they're causal. Yeah.
All right. Thank you so much.
Thank you.
Okay, thanks. Thank you. So we have the room until 11, and since we started a bit late, let's continue and we get the coffee afterwards, right? Yeah, the coffee is here. It's here. Okay, great. So then I would like to introduce Raquel Fernandez, who is our next speaker. Raquel is a full professor of computational linguistics and dialogue. Is also the vice director for research at the
Let me get this. No. Now, yes?
Yeah, okay.
All right. Okay, so thanks, Evangelos. And yeah, I'm glad to be at the workshop. Very interesting so far. So in my group, as Evangelos was saying, we do also quite a bit of research on multimodality, combining computer vision and NLP, as well as other things, conversational AI, etc. Today, I was stuck here with the label language, right? And I'm very happy to take it as well. So I'm going to focus on a project that is really only about language. If you are interested to talk about other things that we do in the group, then I'm very happy to talk afterwards. But I'm going to focus on a project that I'm quite excited about, that is about language. And so this will be a rather focused talk on one specific piece of work that has just come out very recently. And here's the title: Evaluating Uncertainty in Neural Text Generators Against Human Production Variability. So what's this all about, right? So we have all these very powerful language models that are able to generate language. So we have all this generated language, but how do we actually evaluate the goodness of this language, right? So there are many ways in which we may want to evaluate this, for example, with regard to whether these models output correct information, with regard to their accuracy, whether that's of course very important, right? But there are many other properties of this language that that are important as well, right? And as we in NLP know very well, evaluation in natural language generation is actually very difficult because there is so far nothing that works better than human evaluation, right? So in this work, oops, now I cannot go on. Now, here we go, right? Which is a collaboration with several people. This is led by two of my PhD students, Mario Giulianelli and Joris Ban, and together with colleagues Wilker Assis and Barbara Planck. What we are doing is looking into evaluating the uncertainty of language models of text generators more generally through the lens of human production variability. Okay, so let me tell you what I mean by human production variability. So the way in which we can communicate and express the same ideas in language as humans is very varied. There is a lot of variability. And there are many sources for this variability as well, many reasons for this variability, but one key variability is that in different communicative situations, we may have, like communicators or speakers may have a variety of different intents, of different things that we may want to communicate. This is particularly visible in the context of dialogue, right? So if we have a context, a bit of dialogue like this one here, can you help me please? Sure, if I can, I want to send this email, this small parcel to Canada. There are many ways in which we can continue this conversation that would make this dialogue coherent, right? So here there are possible 5 ways in which this conversation can be continued that have been provided by actual speakers or well, not really speakers, but Turkers here that were continuing this dialogue online, right? You can go on by saying, so, yeah, so what do you want me to do? That's a question, right? So it's a request type of intent. To whom? Another question. It takes 10 to 14 working days to reach, so sort of informational intent. Okay, can I get the address, right? So it's clear that there are different intents that we can use to follow up in this context. So one source of variability is the multiplicity of intents. Of course, this is not as relevant in all possible communicative tasks, in all possible generation tasks, in all possible production tasks, right? So the number and variety of plausible communicative intents depends quite a bit on the production task. In dialogue, it is very prominent, right? In other tasks, it might not be so prominent, this availability of different possible continuations, of different possible productions, right? But even if we were to fix the context, like the dialogue context that I gave you before, and the intent, for example, if we are in a communicative situation where the intent is clearly translate this sentence, right? So we are fixing the context, the input sentence, we are fixing the intent. There are still many possible ways in which we can express the same intent, right? So there are many possible realizations of a given idea, of a given intent, right? So this is very well known in the study of human language production, right? Here you have an example of, this is a translation between English and German, and 5 possible translations provided by 5 different translators. And you can see how they are all slightly different, right? Like, for example, this phrase, several companies, can be expressed in different ways in the different translations. And this other piece of text here, reacted cautiously, can also be expressed in different ways. All right, so these are at least 2 possible sources of variation in human language production, intent and surface realization, provided that we have fixed the intent. And just to make a note that this is true, this variation is present not only at the level of human populations, right, that several individuals can say different things at different points, but also at the level of the individual. If you ask the same person at different moments to translate a sentence, they actually may come up with different possibilities. So it's really very present and very much part of how human language production works. All right, so we are interested in defining a framework for probing the uncertainty in natural language generation models through this lens of human language probability, right? So we want to, in a way, so we think that if a natural language generation model is meant to be a good representation of human production, human language production, then there should be some connection between these two aspects, right? It is the uncertainty of the model and the variability that we observe in human language production. Okay, so if we have, in abstract terms, a text generator, like a large language model, right? So this text generator is going to typically be made up of two types of mechanisms, right? Two mechanisms that work together. The underlying statistical model, right? And also a decoding algorithm that will, in the end, produce sequences of tokens of words for us, right? So these mechanisms specify a probability distribution over sequences of words, as I was saying, given an input context, a defined input context. And this probability distribution over sequences of words can be regarded as the uncertainty of this model, right? So can be regarded as representing the uncertainty of this model given a fixed output. So now what we ask is this representation of uncertainty of a given language generator, of a language model, in compliance, in line to what we observe in human production variability, in human production, basically, right? With the variability that we observe in human production, as exhibited in populations of humans, right? Okay, so these probabilities, right? So this probability distribution of what's present at the model and also what's present within the human population is not something that we can directly observe, right? So we cannot directly compare the two probabilities because we cannot observe them directly. So, but of course, what we can do is to sample from these probability distributions, both at the model side and also at the human side, if we have the right type of data, which might not be so easy to come by, but we do have it a little bit. All right, so instead of comparing the probabilities directly, we are going to sample from these probabilities, and then we propose to sort of reframe the comparison of the two types of uncertainty by defining some metrics, right? Some real value metrics that will compare random draws from these processes, from these probability distributions, right? So we sample from the distribution, we get the production given a certain input, and then we get another production that maybe comes from a different process or from the same process, and then we compare these two productions, right? And this comparison, I will tell you in a moment which metrics we are using, but then this metric of similarity or distance is we are going to take it as a measure, as a real value measure of the amount of variability in this generation process. Okay, if you're following me. I'll tell you about the metrics that we are using, which we are calling production probes, but of course, they can be different others that you might be interested in, right? So these are supposed to capture just different dimensions of variability that we are interested in. And I think that this is pretty interesting because it allows you to look in a more interpretable way at the type of variability that is present. It will become more concrete as I tell you about the probes. All right, so we have imagined that we have our metrics that we can measure with this real value, these dimensions of variability. Then we might be interested in different types of variability, right? So one of them would be quantifying the variability in the human productions. So we are sampling from the human process. The other one can be quantifying the variability in the model. So we are sampling from productions that the model is giving us given an input, right? And of course, we could also compare the two of them, but I'm going to focus on the first two ones, right? So we will have these notions of variability, and then I'm going to compare the distance between these two. Excuse me. Right? So just to give you more of an idea of what I have been saying, so imagine that we have here some human productions given a context, given a dialogue context. These are some possible human continuations. These are some generations that the model has output given this input, right? So we can quantify the variation across these ones here, the variation also across these ones here, and then we are going to use a statistical divergence measure to check, to quantify how much deviation there is on the model side from what is plausible human variability, right? Okay, so far that was a gist of the framework that we are proposing. now I just want to give you a few empirical results of applying this framework using certain production probes and a few data sets and a few models to see what are the kind of empirical insights that we can get from this kind of framework. So the production probes that we are using, like the metrics that are going to help us to quantify variability along different dimensions, are these three, but as I said, this can be different things, right? Lexical similarity, syntactic similarity, and semantic similarity. So lexical similarity as overlap between n-grams, between words. Syntactic similarity, very simplified, as overlap between part of speech n-grams, right? So things like nouns, adjectives, verbs, etc. And semantic similarity, we take sentence embeddings and then we quantify, well, sequence embeddings, they don't need to be sentences, and then we quantify, we just compute cosine similarity, right? So this gives us three measures for quantifying similarity or distance variation between productions. Okay, we have our probes, so now we need some data to apply them to, and we are going to use, we use 4 production tasks, 4 natural language generation tasks that may have slightly different properties, so they are actually quite interesting. One is translation, so I may not read all this information here. I hope you can just take a quick look, right? So the 4 tasks: translation, storytelling, text simplification, and open domain dialogue. In all cases, we are using data sets that include several human productions. This is not that common, but there are a few, right? So you can see here, for some of them, there are 10 possible human productions. For some of them, there are only 5, but that's a bit, right? So this is like a sample of the human productions from the population. So these data sets give us the samples from the human production process, and then we use the models that you see here for extracting model-generated samples for these tasks, right? So we are using here different language models. Basically, the criteria that we use to select them were that they are all publicly available models, that they are reasonably sized, and that they are also considered good models for the task at hand. So that's why we don't use a single model for all of them, but just one different model per task. Okay, so we are dealing with these 4 tasks. Now, the first thing that we can do with the framework that I presented is to check for what's the amount of variability in the human data. In my view, that's already pretty interesting. I think that's already quite interesting from the point of view of analyzing the human production. So we are just going to use our probes, this case here, for checking how much variability there is in these different types of generation tasks in the human generated data. And so these plots give you an idea. The first one is on lexical similarity, the second one on syntactic similarity, and the third one on semantic similarity, right? And you can see the different tasks here, right? So I think the first thing to note is that there is indeed quite a lot of variability in these human productions, right? So no variability would be values on 1 in the x-axis, right? So that would be total similarity. That would be no. I know it's a bit confusing, but that would be maximum similarity. So no variability at all. So we see that there is quite a lot of variability, and that also there are rather different trends with respect to the different tasks, right? So for example, the translation and simplification, the blue and orange here, they all have low levels of variation, right? This is not surprising, I hope, because these tasks are a bit less open-ended, right? So they are also intended to preserve semantics. So they are tasks that are semantically preserving. If you are translating, you want to keep the same meaning. If you are simplifying a text, you want to keep the same meaning. And this is really reflected here, right? So the level of variation is much less along for all the probes, even though there are a few differences, right? While when we look at story generation or open domain dialogue, then we see how this shifts and there is more variation, there is more open-endedness, right? So there is a possibility of having more variation. It's a bit different for the 2 tasks, right? Like for example, for story generation here, we see that there is more lexical overlap between the different stories than what we see in dialogue, right? Possibly because the stories maybe contain the same elements given a prompt for generating a story, right? So if there's a prompt and I tell you, please generate a story that happens in a forest and someone finds a house, right? So the forest and the house are likely to occur, right? While in dialogue, we have more open-endedness than that, right? So bottom line, there are differences, right? There is variability, and also there are differences depending on the communicative task, depending on what's the generation task, basically. Okay, so that's what we get when we look at the data. Now, do neural text generators reproduce human production variability? Are they able to, are they sort of well calibrated with respect to human production variability? So just to remind you, right, what are we doing? I show you results for this kind of measure here. Now we are gonna get the productions of the models, and we are gonna quantify the distance between these two, okay, the divergence between these two. So this plot here gives you an overview of what we get. So this is distance. So values centered on 0 would be that there is no divergence at all, that the model is very well calibrated, if you want. While divergence from 0 then indicates that there's some problems of overestimation or of underestimation. And what do we see? So the first two rows correspond to translation and simplification. And what we see is that the model tends to underestimate variability, right? While for the other two type of tasks, story generation and dialogue, the model tends, at least for some props, to overestimate variability, right? So this is actually quite interesting, I think, and perhaps not totally expected, because we see that for the tasks where actually there is less variability in humans, the model goes towards the extreme. So it actually underestimates variability. So it's even more constrained and than what the humans are. And for the tasks that are very open-ended, the model in fact overestimates variability and produces things that are even more different than what humans would produce, right? I want to point out that this is also not extreme, right? So we don't see huge divergences, so it's not too bad, but we do see these trends quite prominently, right? Okay, so this is one of the main results. I just want to now show you a couple of examples that exemplify these trends, right? Where we see that there is underestimation on the one side and overestimation on the other. So for example, for underestimation in translation, so here, this would be the source sentence that we have already seen before, right? So we see that the model tends to underestimate. So it just produces very, as you sample from the model, it produces very similar things, right? More similar than humans would. So remember the example, right? So that, for instance, that for this phrase, reacted cautiously, the humans would produce a variety of things. When we sample from the model, if we sample 10 times, actually all the times, all 10 times, the model produces just this single translation, right? So this is an example of underestimation of the variability. For open-ended dialogue, that's the other extreme, that is actually overestimation. So for example, for this dialogue here, would you excuse me for what? I've got a business call that I really need to take. The humans typically, in the 5 responses that we have in this case, produce these very short responses that they are a bit different, but they are all not so different, right? So, okay, please, well, go on. Sure, why not? Sure, exactly. So they are, while the model in this case sometimes just produces statements that, well, are not only longer, but they are also a little bit out of context. Like, for instance, this one here, you don't need a business call, you need a friend. So this is quite different, quite different from what you see in the human types of responses. All right, so these are just a few examples of some of the main trends that we observe. I'm summing up already. Hope that I'm perfectly on time. So we have presented the framework for evaluating neural text generators in terms of their ability to reproduce a human production variability, right? Which can also be considered as uncertainty in the data. So we are sort of evaluating the uncertainty of the generators in terms of the uncertainty that is present on the data, like aleatoric uncertainty that we observed in humans. And the main findings of this study, I only highlighted the really main things, right? But are that language models tend to overestimate variability in more open-ended tasks and underestimate it in more constrained tasks. And I did not present any of these results, but we also have experiments that have to do with varying the decoding algorithms. And what we see is that that this actually does not have so much of an impact. So variability is an intrinsic property of human language production. We tend to sometimes forget this, but we actually have a lot of variability in how we produce language. And maybe how we set up our generation task is not always optimal. Right? So often we collect only one reference for input and we only evaluate one generation from the model, right? So that might not be the best way of evaluating models, right? Okay, I leave it here. Thanks a lot. And I'm happy to take questions.
Okay, we have time for questions.
Yeah, thank you very much. So I have a question because I'm quite surprised because the large language model by changing temperature, etc. So I would expect that actually variability is way larger than for humans. And so is it that there were some specific hyperparameters or this is
well, so as I didn't present these results here, but we do play with the type of decoding algorithm and also with some temperature scaling and so on. And the effect now, I'm not sure I have on top of my head the results of that, but the general results were that this does not have a huge impact, so that the underlying statistical model has more impact than the specific decoding algorithm that you are using, right? And yeah, so regarding your intuition, I think that this does show that this overestimation that you would speculate that happens does not always happen. Sometimes what is being produced is very there is a small range of things that can be produced.
And I have a follow-up. So then, because this Wasserstein distance is differentiable, I'm not 100% sure about like use BERT, so this is differentiable as well. So then, can you use that as an objective?
Yeah, that's really nice. So, okay, I didn't put many things here about what you can use this for. Hope that you also have your ideas. I think that that's a possibility, right? So you may want to have some targets, because a question that I was maybe also expecting, let's see, is like, well, but why do you want your models to reproduce human variability? Do you always want it? Is that always desirable? Well, I'm not sure. We can discuss about that. But maybe you have some targets of what kind of variability you want to use, right? And then if you could just include this as an objective, then I think that that would be great. Or even create some sort of reward in a reinforcement learning setup, right?
Okay. Any further questions? Yeah. Maybe you can start the microphone.
This question is you don't have my question.
Okay.
Why should the machine variability be
there you go.
Correlated with the human variability? But the other part of the question is also about model calibration, right? So right now the probability of sampling from the next token from the language models, right, might not be the best way the model is, best depiction of the uncertainty of the model, right? So if there are better calibration techniques, meaning the probability is reflective of the uncertainty of the model, then does it actually change the analysis?
Well, okay, let me maybe start here and then we go to the other question. I mean, how you decide to represent the uncertainty of the model, there is not only one option, right? I think this is an open question, and yeah, it's it's not straightforward, basically. You can take your choices on how you represent uncertainty of the model. Because if you choose something that is very different from this, then yeah, this analysis would not hold. Here we are arguing for a certain way of representing uncertainty. Yeah, which we think makes sense, but we could. So I think that's as much as I can see. So if you have a different representation of uncertainty, it may not fit with what we are proposing here.
On the other hand, it might be an opportunity, right? So if you want to tune the model or calibrate the model according to the uncertainty of the human, maybe we get something interesting out of the model.
Yeah, okay, but Okay, maybe I'm not getting exactly what you said. Maybe we can talk about it afterwards. Okay, but then very briefly to go to your more main question, why we may want to do that. As I said, it depends, right? I think personally that there are some good reasons for this. Like, for example, I'm interested in having language models that are also useful for investigating psycholinguistic questions, right? So I would like them to be a good reflection of human production processes, right? I think that there might also be more applied goals for these. You may want the human to behave in a way that comes out, that comes across as natural and more human-like. But as I said, the framework goes a bit beyond that, right? So if you have particular targets of variability that you want to address, that you want to achieve, right? Then this allows you to at least check, to evaluate whether that's the case. Then for different NLP tasks, there might be different targets, right? So I don't know, for example, for question answering, you may want to not be too varied, but actually be to the spot and answer what is true, right? And that might have impose some constraints.
Any last question? If not, let's thank you. All right, so our last talk the morning. Xiaolan Zhu. Xiaolan is an associate. I'm not sure if I pronounce the name correctly, but you will.
It's good. Yeah.
Is an associate professor at the Electrical and Computer Engineering Department at the Queen's University in Canada. He's also faculty affiliated with the Vector Institute for AI in Toronto. He leads the text analytics and machine learning lab there, publishing in NLP and machine learning venues. And he's also co-chair. He has done a number of central exercises. So the floor is yours when you're ready.
Thank you much for the nice introduction. So can you hear me at the back? Or we can just show. Okay.
You get the speaker as well.
Sure. So I think I haven't connected yet, right? Sir.
Are you sharing your screen at the moment? On Zoom? There we go. Great. Yeah.
Okay. Just make sure. Can you hear me back? Thank you much. So my talk today is like a more on the application side of the large language model. The title is several studies on large language model for financial and legal text analytics applications. So we know like a large language model has shown impressive capabilities as a general purpose problem solver, because many people, when train the model, they have these goals to train something which can be used in different situations. Specific for many applications we care about, for example, especially some high-stake domains like finance or legal domains, or probably you can imagine medical domain as well. So people care about like how effective they are in those domains, those generic training model. Even if we don't fine tune it, how effective they are. And also like what's the limitation of them? I think people are still like collect more evidence, and we are among them to collect more evidence in some domains we care about. So one of these domains is like a financial domain. So I'm going to talk about some our observation here today to share with you. One is we're going to talk about like to let ChatGPT before to take CFA exams. So CFA is a quite standard exam for a chartered financial analyst. So basically, it's have 3 levels. Level 1 and level 2 are both multiple choice questions. Level 1 is like each question is by itself, standalone by itself. And level 2, like they group it's called vignette. So each vignette is a set of questions. They give you cases. There's more details. You need to analyze a question and analyze cases to give the answers. So we actually conduct a quite comprehensive study. So that we just post this paper on archive a few days ago. If you check yesterday, Hugging Face actually picked this paper as one of their daily papers yesterday. So basically, I can summarize what our finding over here, observation over here. Again, this is a collaboration with JP Morgan AI Research, and I think some colleagues are in London, some colleagues are in New York. So basically, let me start from the overall performance of some overall observation. So this is we use the ChatGPT for level 1 and level 2 questions. If you can see the performance in general, the performance is roughly in the range of the 40 to 70. So basically, we try zero shot CUT chain of thoughts, and also different a few short setup. Different a few short, we random sample examples, or the 10S means we actually for each subcategory, because the CFA actually have multiple category tasks, including like ethics. You can say they have ethics questions, financial analysis methods, economics, and financial statement analysis, many questions. So if for each subset, we actually sample question from each subset. So basically, this is the overall performances of the models. You can see in general trend, like a GPT-4 is way better than ChatGPT. And also for level 2 and level 1, level 2 questions still harder than level 1 for machine. So then regarding whether the machine pass the exam or not, because the CFA does not publish their like minimal passing scores. So we estimate this by using Reddit communities, like say when people report their score to pass it, we take some average, like basically roughly for level 1 questions, like if you pass at least 60% of each topic, like remember we have 10 topics, and the overall score is at 70, we consider the pass in our study. Again, this is quite an arbitrary selection based on our investigation over Reddit's community. So for level 2, it's a little bit harder. So you achieve at least 50, and then our overall score is at least 60. So it's called a pass. So based on this criteria, you can say like ChatGPT do not pass many of them. The GPT-4 actually pass most of them. There's some unclear case here, like which means basically about borderlines. The model do well in some topics, but it's not doing very well in other topics. But again, so this is the brief summary of the observation. But a more important question, what does that mean? So for me, I think that means several things. One is like again, so because of arbitrary of choosing the parsing criteria, I think we have to be careful about making conclusion of here. But one thing we can see is like the model actually quite impressive, because like it's even in some cases not clear pass, but again, so it's around the borderline pass all the exams over here, especially for GPT-4. So that's first of things I think is amazing. With the model become larger and larger, you can imagine in the next several years, probably larger model is going to be there. So the performance is still going to be getting better and better. So what does that mean? Does that mean computer can actually serve as an analyst? I think that's another very different question, because like the task is designed to test human beings, and test human beings don't have different strengths, different from machine. So while the task can say, okay, if they pass this, they can serve as an analyst. I think that's still an open question. Again, so we just collect some information here to say the performance of large language model on some specific domains we are caring about. In terms of more details, like a subtask, we see the model, again, so probably you don't want to go to the details of those. If you're interested, you can check the paper. They have poor performance in financial reporting and portfolio management topics. The reason is because those tasks are more case-based, it's more applied, it's more computational, requires some calculation formula, and it's more CFA specific. They also include more structured data and the complex details to comprehension. So for those kind of tasks, the large language model like ChatGPT, GPT-4 still short behind compared with the other category of tasks. Again, so it's perform much better in corporate issues and the derivatives. Here, derivatives not mathematical derivatives. It's not mathematical derivatives. So in those tasks, basically, they rely on the concept, and there's often have the clear mention concept. They are doing better. So again, so this is one another observation we made from this data set. So compare level 1 to level 2. So basically level 2, this is level 2 result, level 1 result. Level 2 is still worse. So level 2 questions are grouped into item sets. And it's go deeper to about specific financial topics, need to more specialized problem. And level 2 prompts are much longer than level 1. It's often 10 times longer. I mean, even large language model can handle very long prompts, but we feel still like if the information is diluted over a long text, it's more challenging for the model. So also level 2 feature a high proportion of questions require calculation and a question containing structured data like tables. So in terms of error types, so most of the errors relate to knowledge. Here, knowledge means like there's some critical knowledge the models do not have yet, like to solve the problem. The second is like even model have enough knowledge, they still make mistake by reasoning things away. One category we think we found is like the model hallucinate. The model hallucinate by think, okay, the question have some assumption or has some information required. So based on that assumption, they make inference. So that makes a lot of trouble for the models. And also the model have make mistake on calculation. And I think recent tool use methods can be used here to solve those kind of problem. But again, so the knowledge, how to knowledge, solve logic, this type of problem or reasoning problem is still hard is still hard. And interesting, there's a lot of inconsistency problem, like the model do the reasoning very well, and every step is right, and the last step they pick the wrong answers. So it's quite surprising, even in GPT-4, they still make a lot of mistakes like this. I think this part is easier to fix. And this part, by using tool use, is easy to fix. The reasoning part and the part of knowledge part is still hard. So we have more analysis in the paper, you can check it. And actually, we conduct more comprehensive study, not only for CFA, but also for a wide range of financial analytics, text analytics tasks. From sentiment analysis to QA. We use models fine-tuned for financial domain or model actually pre-trained on financial data like Bloomberg GPT. And those models, we compare them. There's more details about those, but I just summarize some findings over here. So first of all, ChatGPT and GPT-4 significantly outperform others in most all tasks, except AER, those kind of structure prediction problem. I think Dan also mentioned some of this kind of things in yesterday, like for AER, I think for those structure prediction problem, my feeling is the model is not trained for that. But again, so I think there's some interesting implication for this kind of observation. Because some people believe like so far in terms of data knowledge representation, we represent a knowledge like in distributed way in language model, but whether that's the best way to represent knowledge, especially if you want to get some like explainability. So some people like I think Hector Vick in University of Toronto, who is a PR guy. So he basically mentioned language is a very good source, probably one of the best source to represent knowledge. But again, to use that knowledge base, it's still hard. So one way to use that and to make the way to use knowledge is explainable, is to extract knowledge to represent it in a structured ways. I mean, there's a traditional like information extraction ways to do. So far, I think if the model is not doing well in AR, I mean, then maybe there may be many different reasons, or even like relation extractions. I think there's an implication that if we really want to the model actually to understand relations, to extract, to represent the information in that ways to improve the explainabilities, whether the current model can do that or not. The second things we found is both models performs better on financial NLP tasks than SOTA language models actually specifically trained on financial corporate. Like again, so this generic trained model actually performs better in many of these tasks on models that pre-trained on the financial financial data, like Bloomberg GPT, which is very interesting. Because I think one reason is like even we think like if we pre-train a model in financial data, but again we cannot have an expert which only is expert in financial data. They should also have common sense to make some decision together. The third is GPT-4 consistently show improvement over relatively simple tasks. But for more challenging tasks like relation extraction QA, GPT-4 can introduce actually more performance drops compared with ChatGPT. So GPT-4 actually show very good performance on even those better improvement on the more challenging tasks over here. Again, so we have more detailed analysis in the paper, but because this paper is going to publish in the EMLP's industry track, we gave some suggestions like so far seems GPT-4 could be the first choice for financial NLP task based on the study over here. So this is our recent investigation. I myself are also working on like apply NLP and large language model for another domains, which is like a legal domain. So over based on some like study, like over 67 of legal professionals believe like a generative language model AI will have either a transformational and high impacting change on their profession. They actually, the firms in the legal department across public and private sector cite operational efficiency as a top priority over the next 18 months. So we are working with colleagues in legal in law schools to work on some of the interesting problems. We have a project for open justice. We want to make some open source legal QA questions to public. So to hopefully they can reduce the cost that people use to access the legal services. So actually, this is a collaboration with Samuel Dahan. He's a law school professor. He actually is I think is a cabinet member of the Court of Justice in European Union here, also an advisor for like a EU Commission over here. So we work together closely in the last few years. So basically, we try to train the user, grab the pre-trained data and adapt them on very good quality data with very good quality. This data is available. We have like a different source to get this data, and then we further train provide the model to users to collect their feedback and custom the models to different users. So our hope is open source this. And we have many different collaborators, like in US and Canada, and even some of them in Europe and Asia. So we think there's several problems that need to be solved. One is hallucinations being a problem. The second is citation. We need to get a good citation for generated text. The third is reasoning. And the fourth is multiplicity. Multiplicity means a model lack diverse narratives. Basically, lawyers often said it's like if you give them a case, lawyer often said, okay, it depends. So it depends on like many situations. The case can be explained, can be the decisions depend on many situations. The current model we want to encourage them to give more diverse potential solutions for the case. But today I'm going to focus on just talk a little bit about the citation and the reasoning. We have students working on different of these subtopics. For citation, we have a paper in this upcoming EMA finding. So basically, we propose a task and do legal citation prediction based on both precedents and also legislations. So basically, this part is called a provision. This is a precedent. Basically, we want to use both information to help us to make the decision to find a citation. Basically, during this process, we also want to align this decision process with expert thought process. Basically, expert rely a lot on precedents to enhance their, like lawyer rely on this and enhance their argument. Like the judge also rely on this when they write their opinions. And then we need to put them together to make a prediction for a legal citation prediction. I'm going to be very quick on this part, but again, so you can check that paper. The key idea is like we want to force the model not only to make this make a prediction, but also force them to be close to some of these to try to use a prototype cases, because lawyer did a lot whenever they have new case. I mean, I'm not an expert of the legal domain, but by collaborating with my colleagues, the lawyers have really rely on like a prototype of the previous cases and the prototype of provisions to make their decision, to strengthen their argumentation, to strengthen their arguments. So basically, we want the model also try to to leverage prototype by clustering the training cases as prototypes. So basically, the model's key idea of the model is try to clustering the training cases into prototypes. And then we will make a prediction which we want to use that information to say, okay, that prototype contributed more to this decision. So we want to do that. By doing that, the model actually performed well, and also in visualization, the representation is more well organized. Okay, so this is the citation part. I also want to talk briefly about the reasoning part. I think Dan yesterday talked a lot of the reasoning. Also, reasoning have no very simple definition. But in the past few years, we work on different form of reasoning. We actually compete for the original Winograd test in EJCI, I think is in New York in 2016. That's I'm one of the contributors of this system, which is very barely passed a random guess at that time. It's one of the best systems at that time. And during the last few years, the model performance increased a lot for reasoning. So we work a lot also on natural language inference problem. We propose this ESM model, which is widely used for fact verification and reasoning. But again, so those are already so far it's already a yesterday technology. And we're also working on table-based reasoning tasks. Again, so during the last few years, I myself view the improvement of the model performance dramatically. I feel excited, but also I feel what's the next step we should do? So there's some different opinion. In my group, we are working on some neurosymbolic models. So basically, we propose some neurosymbolic model, try to combine the advantage of the distributed representation with some symbolic representations. So this is a paper published last year in TACO. So we try to, when we do make a decision about natural language inference, we try to combine the neural networks with one type of logic, which is natural logic. We pick that one because that one has been developed for NLI for many years. I think one example given by Dan yesterday is actually also involved in this kind of logic. For example, if I said every people in the US is higher than me, and then every people in, for example, Arizona is higher than me, right? So this is like example of downward monitor, because every people in US entails every people in Arizona. But this is downward monotone because you pick the more restricted concept, the entailment still satisfied. In upward, you have to use a less restrictive. If I said, okay, I dance today, then it also entails I move today, because dance is a type of move. In that case, you replace the word with less restrictive word, and the entailment goes. So basically, it's dependent on context. Sometimes you need to replace the word with a less restrictive. Sometimes you need to replace with more restrictive. So natural logic is based on those kind of concepts. So we put this model together again. So the key idea is a low level to represent the meaning of the words, to represent their relationship between words, whether a word entail another word, they are equivalent. We use neural models. But top level, we use some logic format. So our belief is that logic can be used to regularize the model. It also can be used to build a backbone. But I personally like the second one, because I think if you just use logic to regularize the models, neural models, it not give you the building explainability. So this is one work I just briefly mentioned over here. But again, so this is a more recent work is in this year's ACO, we try to build a natural logic attack based on natural logic that attack to the current models. I think the key idea is use the same logic format, natural logic, we try to replace the word within that logical formalism and build the attack examples and use the examples to attack model. We hope this kind of work can help us to understand the weakness of current model. So this work is in this year's ACO. So to summarize today's talk, I start from some applications like what language model can do, what language models still are limited. So there's two limitations. One is knowledge. So the second is reasoning. So we conduct some work on this. From the knowledge part, I think reasoning model like retrieval-based model and the tool user can be used to enhance it. And for the reasoning part, I think it's probably the very hard part is like basically we try to find some solution. One solution is to combine the logic with neural models, but still seems there's a lot of gap that we need to fill. Okay, to summarize today's talk, and this is a very brief summary, and thank you very much.
Time for one of the questions. Are there any questions? So I wonder if you think that a success or mild success on this test, the CFA or the logical one, do they have any meaning with respect to doing well on the job? Because basically these are natural language understanding tasks. Why does it mean that the model can do the job consulting or solving financial problems that companies really care about?
So your question, just to make sure I understand the question, your question is like you expected the models actually should solve this kind of problem.
No, what I'm saying is that even if the model does perfect on the test, I doubt that they can serve as good financial advisors and can solve problems, realistic problems that companies care about in the financial domain.
Yeah.
So I don't see the correlation between the test, because the test is designed for humans. And what we show is that the model can understand natural language to some extent. But why does that mean anything from the perspective of being a realistic financial advisor?
Yeah. So do you want to share like some example, like what's the gap you still envision over there between like this task and the final can replace humans with agent?
So there are many things that a financial advisor need to do from the perspective of doing predictions, doing mathematical problems, being 100% accurate. I mean, 70% isn't good enough in these cases. So I don't really understand. I mean, you give examples of relation instructions and NER. People do this 100% basically. So the fact that the model is doing better than yesterday on this doesn't make them better financial advisors.
Yeah, first of all, like I mentioned, two works. Like one work we did is like for test ChatGPT for like 8 different tasks of NER.
No, I'm not questioning the work. I mean, the work is very interesting. What I'm trying to understand from your understanding of the tasks, do you think that scoring well on these tasks is really a reflection on the ability of the models to actually serve as financial advisors?
Yeah, so basically, in addition to that, a task, like you said, we test on this CFA test. So this CFA test is designed for human beings, to test human beings. We know human beings' definition have different strengths, right? If you test the human beings' memory, so human is not as good, not going to be good as again. So, but those tasks, I think, is designed to solve, for example, the level 2 task. It's designed to solve a give you special case. You gave me answers to answer those questions based on those cases. So if machine can do that, for example, more like a 70%, some days like a 90%, 95%. Let's suppose that in ideal situation, they do it perfect, 100%. I feel like the model could be failure in some cases to replace some job of financial analysts. I think that.
What if I train the model on this data? I just show the model the tests and the solution on the test. The model will do 100%. Does it mean that it can serve as a financial advisor?
Yeah, so that's a related to 2 sub questions. the first question is like, when we do this, we are very careful like, to remove the data pollution part. Because we do a task like based on some previous work, to do a task is make sure that the data is not polluted. So that's the one step we do. We describe how we do that in the paper. Basically, I guess here main idea is like we give the task, remove some task, often more scary the user work. If they are doing very well, means the data is probably already polluted. So that is one sub task. And back to your second sub question, I think is very important question. It's like even the model 100% pass a test. I believe we can replace some job of analysts, but are we going to replace all of them? I think that's a question. Because even model pass all tasks perfectly, we still have their short back. And that their short back is taken from human. Right. So I think that difference may have an implication that even the model pass 100% someday, whether they can replace human beings.
So what is missing?
I think for example, some kind of promises, if you some kind of promises, you need to still listen over there. And sometimes like in some special case, like there's always some situations that can be considered, which basically long tail, very long tail problems. That's very hard. The long tails long related to I think based on so long tail is related to like not only the reason, but also like conditionality and also like common sense. So we only talk about common sense so far, but conditionality that is handled the real cases. You have to combine multiple knowledge. And if you even pass a test, I mean, in ideal situation, we just assume it's pass a test 100%. But I myself don't feel that's going to be the case. Just because of reason, there's always long tail problem. We have those. The machines are ready to have.
All right, let's take the speaker again. Just make an announcement and then we can
Yeah, I can show you. You want to connect here?
Yeah, no, I have shared screen.
No, we need to this. Or are you?
No,
I don't Zoom already.
just
Oh, then late.
So this afternoon, there will be a debate on the issues of the development of AI in the future. So this afternoon, there will be a debate on the issues of development of AI in the future. And we will take a poll tonight.
I think you can share.
And so, and you can vote on this, on the issues. So if you can do it right now, you can just go there or just scan the QR code and vote now. So we'll have the voting before the debate, and we'll see what your feelings are on those issues, and then we will have another vote after the debate to see whether people have changed their mind. So thank you very much.
Thanks. All right, so thank you all, and let's have coffee, get some energy, and then we will move to the building across. So take your stuff as well. I mean, the coffee's here, right? Yeah. So okay, we get our stuff and move there.